Hello everybody. Today we'll study external flows and forces on the submerged body. This is unit number 6 of fluid mechanics. In the first slide we can see over here there is a solid body, and on this solid body the fluid is flowing over here. When this fluid flows over here, you can see that there is a formation of boundary layer takes place. And here near to the solid body, you can see here that there is a velocity profile is created. So at this point where we can see the velocity is zero because it is adhered to the surface, solid surface. As we goes on in the upward direction, the velocity goes on increasing. And at this end, at the upper string, there will be the maximum velocity. It is equal to the flow stream velocity. So this is the velocity diagram. Velocity profile is created when the fluid flows over a solid body, and this is the boundary layer takes place. We have seen that, for example, if we are seeing the stone kept in the flowing water in the river, we can observe there is some boundary layer creates on that body above that stone. That something layer on that stone, that is nothing but a boundary layer where the velocity profile we can experience just by at the downside a lesser amount of we can say the force is there, while as we goes on the upstream the more amount of force is exerted on the fluid flow. So this is regarding the external flows acting on the solid body. So it's a very thin layer of solid which is neighbor to the solid body. Okay, having velocity from 0 to the velocity towards the upper string. Because of this, a layer is created that is called boundary layer. Okay, so here again comes the picture of velocity gradient, that is du by dy, and shear stress for the tau. Uh, this is the boundary layer for the flow of the flat plate. You can see over the diagram, which consists of a plate, and the fluid is flowing uniform. Fluid flow is taking place over this plate. This point is called the leading edge. This point is called the trailing edge. The fluid flows over this plate, and we can see there is a pattern of the fluid flow is different at different section. Initially at A to B, there is a laminar boundary layer. B to C, there is a transition phase, and C to D, there is a turbulent phase. Also in the turbulent phase, we can observe here this dotted line, the laminar sublayers formation is taking place. So as at the point A, that is a leading edge, okay, so there is more resistance to the layers of the fluid. The velocity over here is zero. But as we goes on further, the velocity goes on increasing, and we can see at the trailing edge the velocity is more, and we can observe more divergent section over here, that is a turbulent fluid. So for this whatever the boundary layer we can see here by A, E, F, G, this is the boundary layer formation takes place when the fluid flows over the solid plate. It is having a thickness, some thickness. The thickness, that means from this solid body to the layer where there is a highest velocity. This distance is called thickness, bond layer thickness, and it is given by 5 z upon Rex. Okay, where del is the thickness of the boundary layer, Rex is the Reynolds number. Okay, capital U is the free stream velocity of the flowing fluid. Nu is the kinematic viscosity of the fluid. Similarly, what we have seen, the laminar boundary layer, we are having a turbulent boundary layer thickness, and it is given by 0.377x upon Rex is to power 5. So these are the formulas for the thicknesses of the laminar boundary layer, turbulent boundary layer, laminar sublayer. We can see over here this is the formula for the laminar sublayer, del dash. Now, what are the factors which affects the growth of the boundary layer? There are 4 factors which affects the growth of the boundary layer: distance from leading edge, viscosity of the fluid, density of fluid, free stream velocity. Okay, so these are the 4 factors which affects the growth of the boundary layer. There are some terms which are related to the boundary layer. Already we have discussed boundary layer thickness. First term is the boundary layer thickness. It is defined as the distance from the boundary of the solid body measured in y direction to the point normal direction where the velocity of the fluid is approximately equal to 0.99 times the free stream velocity of the fluid. So this is the boundary layer thickness. Already we have discussed. Similarly, another term is the displacement thickness. It is defined as the direction perpendicular to the boundary of the solid body by which the boundary should be displaced to compensate for a reduction in flow rate on account of boundary layer generation. So this is the displacement thickness. Similarly, we are having momentum thickness. So boundary layer thickness, displacement thickness, and momentum thickness, these are the main terms uh, of the boundary layer formation. This is the derivation of the momentum thickness. We are finding out momentum of the fluid through the strip, momentum of fluid in the absence of the plate, then loss of the momentum through the strip by taking the difference and then integrating it. We are getting this equation, plus theta equals to 0 to del u upon capital U, 1 minus 1 upon u upon capital U dy. All these derivations are on the same pattern. Energy thickness, the derivation, and this is the formula for energy thickness. Same pattern, the derivation is there for energy thickness, momentum thickness. The next term is the separation of the boundary layer. You can see here the separation of the boundary layer through this diagram. It is observed that there is a point A, B, C. This is the uh, pattern of the boundary layer, and then again the D, E. So for point A, B, C, so this section is the converging section, and C, D, E is the diverging section. We can see over here uh, pressure gradient, delta P upon delta X. This is the important parameter for boundary layer separation. And from this diagram, it is observed that as the boundary layer increases up to point C, we can see that the pressure gradient goes on decreasing. This is the pressure profile. Okay, so delta P upon delta X is negative, and from point C to E, the pressure gradient is goes on increasing. That is positive, and hence we can see this is a diverging section. There is a separation of the boundary layer from the streamline takes place. This is here we can see by the dotted line. Okay, so pressure gradients work much more is an important parameter for boundary layer separation. Location of the separation of the point. What are the locations? The separation point is determined from the condition d by u by d by y at y equals to 0 equals to 0. Let's go for the what are the various conditions. If d by u by d by y at y equals to 0 is negative, is less than 0, the flow has separated. If d by u by d by y equals to 0, this is the condition, is equals to 0, the flow is on the verge of the separation. If d by u by d by y equals to 0 is greater than 0, if it is then it is positive, then it's remain attached to the surface, will not separate. There are different methods of controlling the separation of the boundary layer. First is proper body design. We can see that the aerofoil shape of the cars is for the streamlining the body. Okay. Next is delaying the flow separation artificially. Flow over the Gulf ball, we can see this is one of the example. Accelerate the flow by providing slots like this, by providing the slot. Okay. Fourth method, suction of retarded fluid in the boundary layer. So here we can provide one slot over here. So suction slot can be there, which will retard the fluid in the boundary layer. And the last one is the fluid acceleration by blowing. Energy is supplied to the retarded fluid by injecting the high velocity fluid from blower. So these are the five methods by which we can avoid the boundary layer separation. So in the next lecture, we'll go for the forces on the submerged body that we'll discuss.